Great. Hi, everybody. I'm Sarah Sue, and I'm another researcher at Aspiring Scholars Directed Research Program. And today, my presentation will be about using an instrument called the NMR, otherwise known as nuclear magnetic resonance, in order to deconvolute the mechanism behind the Biginelli cyclocondensation towards the synthesis of novel trifluorinated pyrimidine analogs as antiproliferative agents. So just a quick overview of what I'm going to be talking about in my presentation. First, I'll go over multi-component reactions and their role in drug discovery. Then I'll talk about the initial discovery of 2,4-dihydropyrimidines and monastrol specifically. Then I'll talk about the role of fluorine in organic synthesis and medicinal chemistry, the progress towards the synthesis of trifluoromonastrol, as well as using 19F NMR to elucidate the mechanism behind the Biginelli, as well as using a Hammett linear free energy relationship to understand what the rate determining step of the Biginelli is. Finally, I'll go into some in silico modeling of these mechanistic pathways. So first, I just wanted to talk about the drug discovery process as a whole. Currently in drug discovery, there are many barriers, but the biggest barrier is the fact that there are so many molecules that make it into in-clinic trials, and most of those compounds are rejected. There are thousands and thousands of compounds that are sent into trials every day, and it takes people years to generate these compounds. For example, me, I have 4 years of synthetic experience, and it takes me around a week to synthesize a molecule. Imagine having to generate thousands and thousands of molecules on scale in order to send them into these trials, and the majority of these compounds don't even work. That's our current drug discovery process. And so what multi-component reactions are able to do is they present this platform where we have these interchangeable molecular parts. And so essentially by using one reaction, we're able to create this massive library of very diverse, complex analogs. We're able to create these very complex scaffolds, which we can then send into trials very, very quickly and efficiently. And so now I'll be talking about monastrol, which is a potent mitosis inhibitor. Monastrol works by arresting cells in the metaphase part of the cell cycle. And essentially it does this by inhibiting a motor protein called kinesin EG5. So essentially, by arresting cells in the cell cycle, it's able to stop the progression of cancer, as cancer is characterized by the progression through the cell cycle unregulated. And so basically, by arresting cells in the metaphase part of the cell cycle, we're able to stop the progression of cancer in humans. And so serendipitously, while monastrol is a good compound, it isn't great. And so what we wanted to do was we wanted to draw inspiration from what many other medicinal chemists have done, which is they have fluorinated small molecules in order to increase their efficacy. So essentially here you can see fluorine on the periodic table. But the reason why so many people use fluorine in these small molecules is because it's bioorthogonal, so it's not found in nature, which means that this improves the metabolic stability and lifetimes of small molecules. Essentially, because fluorine isn't found in nature, we're less able to digest molecules having fluorine in them, and that means that whatever small molecules have this trifluoromethyl group, they're able to stay in your body for longer, meaning you need lesser doses of the same compound to get a stronger effect. And so here you can see just various compounds that have this trifluoromethyl group, and these have been found to be antiproliferative agents. In fact, there's an ACS Omega paper that says around like 20% of FDA-approved drugs currently have a fluorine group on them. And so because of this, we wanted to see if we could fluorinate monastrol to make it from a good cell cycle inhibitor to a great one. And so serendipitously, monastrol is synthesized through the Biginelli cyclocondensation, which is a multi-component reaction, which means that we're able to create this really complex scaffold using just one reaction with 3 starting materials, a benzaldehyde to the left with any aryl substituent. We can have a urea and then a ketoester, and these 3 combine in the Biginelli cyclocondensation in order to synthesize monastrol and analogs of monastrol. And so with the Biginelli cyclocondensation, previously people have reported that it has 3 possible routes, which is the iminium, novanagal, and enamine routes. And we'll be going into those a bit later. But in order to optimize a reaction, you have to really understand the mechanism. And so while people have realized that there are these 3 possible routes, we wanted to kind of understand what the one possible route that the Biginelli actually goes through is. And we also wanted to see how fluorinating the keto ester in the Biginelli would impact this mechanism. So when we ran this reaction, when we used the trifluorinated keto ester in the Biginelli, we actually found this unexpected product. So we expected to synthesize trifluoromonasterol, as seen in the dotted box. However, we found that we did not isolate that product, and rather we isolated the molecule with a hydroxy group near the trifluoromethyl group. Essentially, we synthesized this hextrahydropyrimidine, and we found that we would not actually undergo dehydration unless we used forcing conditions. So without reflux with high equivalences of acid, we were actually unable to get to our desired product. And so this indicated to us further that we needed to probe the mechanism of the Biginelli, because this kind of indicates that it undergoes a different mechanism than what traditional monasterol or LASOM63 is synthesized under. And so now I'll just be going into the 3 possible routes that we probed to see whether or not the Biginelli was undergoing these. So the first was the iminium, wherein you see that the thiourea and the substituted benzaldehyde react first. This forms an intermediate which then reacts with the keto ester to form our desired product. The second route is the enamine route, where we have the urea and the keto ester, and then these finally react with the benzaldehyde to lead to our desired product. And the third route is the Novanagle, where we have the benzaldehyde and keto ester react first in an aldol addition. Then it undergoes a beta hydroxy elimination and combination with the thiourea, and it undergoes an azomichael and a 6-exotrig to lead to the final product. And so what we wanted to see is we wanted to see which reaction was actually happening. But how are you able to look at reactions? Reactions are really small. These are like molecular level. You can't use a microscope to look at a reaction. Light microscopy, scanning electron microscopy, those can probe really, really small objects, but they cannot probe molecules. So what we have to use is this instrument called the nuclear magnetic resonance, as you can see at the top there, otherwise known as NMR. And essentially with NMR, you're able to look at the nuclear spin of atoms, and through that you can kind of understand the structure of the molecules you're looking at. So what we wanted to do was we wanted to use NMR to track these reactions in order to see which reaction mechanism was actually happening. And to do that, here you can see our 19F NMR spectra, and basically we use the fluorine group on our molecules to kind of track the different reactive intermediates in the reaction. And by doing this, by running hundreds of NMRs, we ultimately found that the enamine pathway was operative. Then to probe this further, we wanted to develop a Hammett linear free energy relationship. So basically what this does is it correlates the electron withdrawing character of the aryl substituent of our compounds with the rate of the reaction. And we wanted to do this in order to figure out what the rate determining step of our reaction was. So we generated this library of monasterol hexahydropyrimidine analogs. And as you can see here, there are various different aryl substituents, and each of these aryl substituents have different electron withdrawing character. We then again relied on NMR in order to figure out our concentrations over time in order to develop the rate of each of the reactions. So what we did was we integrated the amounts of our reactive intermediate, our product, as well as our starting material, and we graphed these in order to figure out the initial reaction rate. And then after finding out the initial reaction rate, we wanted to graph this against the Hammett values. So on the right here, you can see various Hammett values. What these correspond to is the electron withdrawing character at the benzoic position. And so after graphing these all together with the Hammett value on the x-axis and the initial reaction rate on the y, we found that for both 3 and 4 substituted aryl substituents, we found that there was a negative correlation between Hammett value and initial reaction rate, which kind of indicates to us that the rate determining step had to be a loss of positive charge. And so to corroborate this further, we used in silico modeling. So we used quantum mechanic calculations, DFT in particular, or density functional theory. And what we did was we basically tracked the single point energies of each of the intermediates in each of the routes. And so here you can see that the red is the enamine route, the green is the iminium route, and the black is the Novanagle route. And so our Hammett revealed to us that the rate determining step was the loss of positive charge, which would be the second to last step, the hydroxy elimination before the cyclization, which correlates with this steep increase in energy for the compounds in the red pathway right before the final decline at the final cyclization. Moreover, we can see that these in silico models also corroborate our idea that the enamine pathway is operative, because we can see that there's an initial decrease in energy corresponding to the enamine pathway. So overall, in this project, we were able to create a platform where we could kind of probe the reactions using benchtop NMR. This is previously unprecedented. Most institutions use large NMR machines, but by using benchtop NMR, we show that institutions such as even our school, smaller institutions are able to probe reactions on the molecular scale. We're able to solve actual pressing issues towards deconvoluting reaction mechanisms and optimizing mechanisms towards creating these massively complex scaffolds, and hopefully we're able to speed up and make the drug discovery process more efficient. So thank you. Here are my acknowledgements. I work with an organization called ASDRP, as well as an organization called Analysis, which creates our benchtop NMRs. Thank you.